Integration by parts is really going to come up in two scenarios. One's where when you're taking the antiderivative and you have two functions multiplying each other. Another scenario is where it might look like you want to use substitution method, but when you apply a substitution method, it fails, kind of like we saw in that one example in the previous videos. When we tried substitution method, but we ran into some issues, that can be a sign of integration by parts. So, lots of pieces here and lots of substitutions. So we're going to be using a variable u and v for doing this. So what we're going to do is take our original antiderivative, that's all in terms of x and dx, and we're going to make these substitutions. So we're going to be choosing a value for u, and we're going to be choosing a value for dv, such that u and dv make up our entire integral that we're starting with. Now we're going to talk about some methods for which one to choose for how this can kind of piece together. But some tips are going to be, you want to choose u such that du is simpler than u. So you want to be making things simpler when we're taking the derivative there. And you want to choose dv in terms of something that's easy to take the antiderivative of. Okay, so, and then from there we apply this formula, so the antiderivative of u dv is equal to u times v minus the antiderivative of v du, which might look like a bunch of gibberish at this point, which is fine. Kind of see how we end up applying it. So, first scenario here, we have the antiderivative of x times e to the x dx. So this is a case where we have two functions multiplying each other. So we have x and we have e to the x. So what I like to do here is I like to start a little table. So a little 4-piece table to help me get organized, because what we want is u du v dv. Now we're going to use x and e of x, and actually 3 pieces here. We have x, e to the x, and we have dx that we want to account for here. When we're making our table, what we're going to fill in using those pieces is we're going to fill in for u and we're going to fill in for dv. So, and actually I might even start with dv here, because now that we've been working a lot with antiderivatives, we kind of have a routine for, or not even a routine, I'm missing the word that I want to use here, but we have an idea of what's easy to take the antiderivative of. Because typically we get a little more stuck with antiderivatives than derivatives. So if I'm looking at these pieces here, taking the antiderivative of e to the x is really nice. Antiderivative is just e to the x. We can take the antiderivative of x, that would be x squared over 2. That just gets a little messy. So with this scenario, in terms of choosing which one I want to be dv, I'm going to use e to the x. And along with that is going to come the dx portion. So I used up those 2 pieces, so I'm letting dv equal e to the x dx. Then the rest has to be u, so u is going to be equal to x. Okay, so I have u, I have dv, and now I want to fill in the rest of the table. So if I focus on the portion with u, if I have u equal to x, then du is going to be the derivative of x with respect to x. So derivative of x is just 1, and then I'm going to have dx coming through there. So what I did there is took the derivative, and let me make a little note of that. So to get from u to du, we took the derivative. Now with v and dv, so we have dv is e to the x dx, and we want to go and find just v, which means we're going to take the antiderivative. So the antiderivative of e to the x is just e to the x. So v is equal to e to the x. So there's my table. We started with finding u and dv. From u we could get du by taking the derivative. From dv we can get v by taking the antiderivative. Just be sure you have your rules memorized, or not even memorized, but have them available so you know you're going in the correct direction here. Okay, so now what we can do is, if we're able to reframe this antiderivative as, oh, I need to remember what the rule is, u dv, then we can simplify by taking u times v minus the antiderivative of v du. Okay, so with our setup here, this antiderivative of x times e to the x dx, well, x is the equivalent of u, e to the x dx is equivalent of dv. So there we can see that equivalent of the antiderivative of u dv. Now what we're going to do is make our substitutions. So u times v, so we're going to have x times e to the x minus the antiderivative of v du. So v is e to the x, du is 1 times dx, and then our last piece is just to simplify that last antiderivative. So we have this x e to the x minus the antiderivative of e to the x dx, which is just e to the x. And then this is indefinite, so we're going to have a plus c on the end there. But that'll do it. X times e to the x minus e to the x. Again, it's all about taking this antiderivative of x times e to the x. So what should happen if you want to check your work is go ahead and take the derivative. So taking the derivative, x times e to the x, we're going to need the product rule there. So we're going to have x times the derivative of e to the x plus derivative of x times e to the x minus the derivative of e to the x. And then the derivative of c is just 0. So we have an x e to the x plus e to the x minus e to the x, which is just x e to the x. So that sounded like a riddle there at the end. X e to the x. So in terms of checking, you can always check by taking the derivative of the answer that you found. Okay, let's go through some more scenarios here, as well as this is a case of a definite integral, so from 1 to 4 of 6x squared natural log of x dx. So I'm going to start with my table, where I would like to have u du, v dv all defined. And we start by defining u and dv so that we're taking the antiderivative from 1 to 4 of u dv. So with this, the pieces that I see, I have this 6x squared piece, I have this natural log of x piece, and then we have dx, which dx is going to go with dv each time. So if we're not finding dv, just dx can go right there. Now, the antiderivative of natural log of x, we don't have a rule for that. So basically, I don't want to take the antiderivative of natural log of x. So that's going to kind of make the decision for me that we want 6x squared for dv. So 6x squared dx is dv, and so u is going to have to be natural log of x. Okay, if u is natural log of x, then du is going to be 1 over x dx. And then dv is 6x squared, so taking the antiderivative, so we'll have this 6x cubed over 3, which is 2x cubed. And now you can make our substitutions. So evaluating from 1 to 4, sorry, my notation was a little off. I want these big brackets here for evaluating this antiderivative, and we're going from x equals 1 to x equals 4. We're going to have u times v, so natural log of x times 2x cubed. So 2x cubed natural log x minus the antiderivative of v du. So 2x cubed du 1 over x dx. So we're taking 2x cubed natural log x minus 2x squared, or the antiderivative of 2x squared, dx from x equals 1 to x equals 4. Okay, so I'm still simplifying in there, and I just need to finish with that antiderivative of 2x squared. So this is going to be in total, we have 2x cubed natural log x minus 2x cubed over 3, taking that antiderivative, evaluating from x equals 1 to x equals 4. So now we can substitute in for x. So I'm going to be taking 2 times 4 cubed natural log 4 minus 2 times 4 cubed over 3 minus, and let's see, 2 times 1 times natural log of 1, which is 0, minus 2 times 1 over 3. And with that, we can just go ahead and plug into the calculator at that point. So let's go to the calculator. Doesn't need to be super simplified before going. So we have 2 times 4 cubed natural log of 4 minus 2 times 4 cubed divided by 3 minus 2 times natural log of 1, which is actually just 0, minus 2/3. And there's our 135.45. So that's our area under the curve between 1 and 4 of 6x squared natural log of x. So we took the antiderivative using integration by parts and evaluating x equals 1 to x equals 4. And that's how we do a definite integral. Okay, let's go through some more scenarios here. Just lots of examples to look at here. So, antiderivative of x squared natural log x dx. And again, with these, I'm recognizing this is integration by parts, not only because that's the section that we're in, but because I have these two functions multiplying together. So that's what's really showing me in these scenarios of I want to use integration by parts. So I want to find u du v dv. Okay, so my parts here, there's x squared natural log x dx. And again, natural log of x, I do not want to take the antiderivative of that. So what you're going to find is most often is if natural log of x is showing up in there, that's going to be your value for u. And so dv is going to be x squared dx. Okay, if u is equal to natural log of x, then du is 1 over x dx. If dv is x squared dx, taking the antiderivative, this will be x cubed over 3. Okay, so we're taking the antiderivative of u dv. So this is going to be u times v, so natural log of x times x cubed over 3, minus the antiderivative of v du. So x cubed over 3 times 1 over x dx. So with this, x cubed, I'm just gonna get that 1/3 out of there, get rid of that denominator of 3. So I'm gonna factor out a 1/3, so that's gonna leave me with x cubed natural log x minus this antiderivative of x cubed times 1 over x, which is just x squared dx. So we have this 1/3 on the outside, x cubed natural log x minus, and the antiderivative of x squared, x cubed over 3, and then plus c, since this is indefinite. And we're done there. In terms of simplifying, you could distribute that 3 through, you could factor out an x cubed, all sorts of different ways of organizing this. So with that, there are different forms of the answer. They're all the same answer in the end, though. All right, another indefinite integral here, x times natural log of x dx. So, making my table, I'm going to have u du v dv. So my pieces here, x natural log of x and dx. I don't want to take the antiderivative of natural log x, so I'm going to have that be u, which means dv is going to be x dx. So if u is natural log of x, then the derivative is 1 over x dx. dv is x times dx, so the antiderivative would be x squared over 2. All right, so if we're taking the antiderivative of this u dv, then what we'll have is u times v, so natural log x times x squared over 2. So let's go x squared natural log x all over 2 minus the antiderivative of x squared over 2 times, and then du is 1 over x dx. I'm going to do that same thing. I'm going to factor out a 1/2 to get rid of that denominator of 2. So we're going to have x squared minus natural log of x. Nope, x squared times natural log of x minus the antiderivative of x squared times 1 over x, which is just x dx. So that antiderivative, so we'll have 1/2, and then in parentheses, x squared natural log x minus x squared over 2, taking that antiderivative of x, and then a plus c for a constant at the end. Okay, 2 more examples here. One more indefinite, one definite. Okay, so this one is the antiderivative of x times e to the 2x dx. So with this one, choosing u and dv. So, pieces here. We have x, we have e to the 2x, and we have a dx, which is going to go with dv every time. So really, that can just go there. So what I want to choose is x and e to the 2x. Where's that going to go in terms of u and dv? Now, something we talked about before is like e to the x is really nice to take the antiderivative of. However, with 2x in that exponent, it gets trickier. So I don't want to take the antiderivative of that. It got too messy with the 2x in the exponent there. It's not impossible to take the antiderivative of, but it'd be easier to take the derivative of that using the chain rule. So, and x is pretty flexible in terms of easy to take the derivative of, also easy to take the antiderivative of, so not too many worries in terms of x, but e to the 2x, definitely more comfortable taking the derivative of that. So e to the 2x is going to be u, which means dv is going to be x dx. So taking the derivative of e to the 2x, we're going to need chain rule here. So we're going to have our inside function is 2x, outside is e with this exponent. So derivative of the outside is e to the x, keep that exponent of 2x, times the derivative of the inside function, 2x, which is going to be 2. And then dx. So du is going to be equal to 2e to the 2x dx. All right, dv is equal to x dx, which means the antiderivative is x squared over 2. And you're done there. Okay, x squared over 2. So if we're taking the antiderivative of u dv, then what we'll have here is u times v, so e to the 2x times x squared over 2. So x squared times e to the 2x over 2 minus the antiderivative of v du. So x squared over 2 times 2e to the 2x dx. So, taking the antiderivative of x times e to the 2x dx. So, I'm going to go ahead and set up my table here. And I want to find u, du, v, dv. Okay, so my pieces here. X times e to the 2x, and then I have dx, but that's always going to go with dv, so that piece is taken care of. Now I just need to choose which is going to be u and which is going to be dv. Now, with u, remember my tip was that if we take the derivative, it should be simpler. So taking the derivative of x is nice and simple because that's just 1. Taking the derivative of e to the 2x isn't terrible, but it's chain rule, so we're going to end up with 2 times e to the 2x. That's a little messier. So what I want to do is I want to try out having u be equal to x and dv equal to e to the 2x dx. Okay, so if u is equal to x and I take the derivative, that's just 1 times dx. Now let's talk about the antiderivative of e to the 2x. There's a few ways you could go about this, and we could actually use substitution method of, like, if we wanted to take the antiderivative of e to the 2x dx. Well, this would be a composite function. So let's say we let u equal 2x, and then that means du is equal to 2 dx. Well, if we do that, then we're taking the antiderivative of e to u, but with this 2 dx, what we would need to do is have 1/2 du is equivalent to dx. So really I need to be taking this 1/2 here. So we're taking 1/2, and then the antiderivative of e to the u is just going to be e to the u. And substituting back in, that's our 2x. So we'd have 1/2 e to the 2x is our antiderivative there. So I know that was super fast, but we could check that real quick by taking the derivative, and you'd have 2 times 1/2 is just 1, and then you'd have your e to the 2x, which is what we wanted. So for the antiderivative, we're going to have 1/2 e to the 2x. Okay, so if we're taking the antiderivative of u dv, we're going to have u times v, so x times 1/2 e to the x, e to the 2x, sorry. So 1/2 x times e to the 2x minus the antiderivative of v du. So we're going to have a 1/2 e to the 2x dx. Now let's go ahead and factor out that 1/2 that's in there. So we're going to have x e to the 2x minus the antiderivative of e to the 2x, which we actually just found already. So with this, we're going to have a 1/2 x e to the 2x, and then we already found that the antiderivative of e to the 2x is 1/2 e to the 2x. And we could leave it just like that. Other ways of simplifying for sure, or we could multiply through that 1/2, but we could just leave it like that. There we go. All right, last one here with the definite integral. Oh yeah, sorry, as soon as I said that, plus c with that last one. We should be adding c on the outside since it is an indefinite integral. Okay, natural log of x plus 1, and we're evaluating from 1 to 2. Now this is a little different looking. This could kind of look like a substitution method one with in terms of having a composite function. All right, last one, and maybe I saved in differing opinions, best or worst for last. So let's go through one like this, where we're taking the natural log, and in parentheses we have an x plus 1. So like I was saying, this could look like a composite function, so we would try to use substitution method. So like our inside function would be x plus 1. But what would happen is we would still be stuck trying to take the antiderivative of a natural log, and with that we get stuck. And actually, to take the antiderivative of a natural log, we need integration by parts. So let's go ahead and walk through how we would do this. So with this one, I'm going to set up my table. This is going to have some steps to it. So we're going to have u du v dv. Now, what differs with this one is there isn't two functions multiplying. This is just a single function. But this is a case where substitution method would fail. So what we're going to do here is, what we're going to have is taking the derivative of natural log of x plus 1. That's not too bad. So we're going to let u equal natural log of x plus 1. So then all we have left over is dx. So that's going to be our value for dv. So dv equals dx. So if u is equal to the natural log of x plus 1, so this would use chain rule, taking the derivative, we would take the derivative of natural log, keeping our inside function of x plus 1, so that's going to be 1 over x plus 1, times the derivative of x plus 1, which is just equal to 1. So 1 over x plus 1 dx. Then if dv is equal to dx, and you could think of that as like 1 times dx, then taking the antiderivative, we would have x. Okay, so there's our setup there. So, and I'm just going to, because really the evaluating from 1 to 2 in terms of the definite integral comes in right at the end. So let's just pretend this is an indefinite integral for now, and then we can evaluate at the end. So if I'm taking the antiderivative of u dv, we're going to have u times v, so x times natural log of x plus 1, minus the antiderivative of v du, so x over x plus 1 dx. So this looks pretty good, but evaluating this antiderivative of x over x plus 1 is tricky. And there's a few different ways to go about it. I'm going to go ahead with the substitution method. So how about, let's do this as side work. So what I'm focusing on is just evaluating this antiderivative of x over x plus 1. So let's go to the side here. I want to make sure I have enough room to eventually take the definite integral. Okay, so antiderivative of x over x plus 1 dx. What I'm going to do is I'm going to use the substitution method here in so many different ways. I maybe think of a different way, but since we've been practicing the substitution method, I just kind of want to bring that in here. So what I'm going to do is I'm going to let u equal x plus 1, and with that, du is going to equal, the derivative is just 1, so it's going to be equal to dx. So when I do that, I'm going to have this antiderivative. I'm going to have u in the denominator, taking du. What's tricky is the numerator. I have an x hanging out there. Now if u is equal to x plus 1, then x is equal to u minus 1, if I just subtract 1 from both sides. So what I'm going to do is substitute in u minus 1 where we had x. So it all works since u is equal to x plus 1. We're treating it the same. It's kind of two different forms of it. Now if I do that, what I can do is divide out u from each piece in the numerator there. So u divided by u is equal to 1 minus 1 over u du. And with that, we can take the antiderivative. We'll have u minus natural log of the absolute value of u plus c, which u is equal to x plus 1. So we're going to have x plus 1 minus natural log of the absolute value of x plus 1. So with that, I'm going to go back now. So I have this x plus 1 minus natural log of x plus 1. So in simplifying, we have x times natural log of x plus 1 still hanging out, and then minus, and that antiderivative is the x plus 1 minus natural log of x plus 1. And we're going to be plugging in values for x, so we don't need to worry too much about our absolute values since we're going to be plugging in all positive values, so we don't need to worry too much there. Okay, so simplifying, x times natural log of x plus 1 minus x minus 1 plus natural log of x plus 1. Okay, so we're all simplified there, and now we just want to evaluate from 1 to 2. So we're going to plug in 2, so we're going to have 2 times natural log of 3 minus 2 minus 1, so minus 3, plus natural log of 2 plus 1, so 3. And then minus, if we plug in a positive 1, so 1 times natural log of 2, minus 1, so minus 2, plus natural log of 1 plus 1 is 2. And we'll go ahead and plug that into a calculator. So, with that, 2 natural log of 3 minus 3 plus natural log of 3 minus natural log 2 minus 2 plus natural log of 2 is a 0.91-ish. That will do it. So with this one, again, so many other ways of evaluating that antiderivative. The substitution method worked best for my brain in particular, so if you found a different way, absolutely cool. But what we can do is mix these methods together. So when we're evaluating the antiderivative here, sometimes you might need integration by parts again. Sometimes you'll need substitution method. You want to keep using all of the tools that we've been building this term in order to take the derivative there.